Hey, honey, it's not working. Oh, wait, there it goes. This computer just takes forever. Hi. I think, I think it's working. Hi, Kenny. Turns out YouTube has two different stream keys for this. I don't know. Goober. Um, I don't know what's going on, but we got it to work. My husband did the same thing I did, and it worked for him. Didn't work for me. So, so I will just sit here, and if people come in the next 15 minutes, then we can have a review session. And if not, we'll go home. I'm munching on my dinner. Fair enough, Kenny. Ask me questions if you have them. Lord knows that might not keep working forever. Been having problems, so. Been a real special evening trying to get this to work. It only took an hour and 10 minutes. I am here tonight with the Onyx. This is the Onyx. This is the one that I mentioned is 1,000 years old. So she's on the bed with me. Okay, until you ask questions, I'm going to eat my sandwich. Now, What's up, baby? Oh, Kenny. Oh, Hannah's here. Hi, Hannah. This, my friend, is a tuna fish sandwich with mustard in it because I don't like mayonnaise, and homemade sweet lime pickles that I make in the summer when my cucumbers are coming in. Joanna Marie Becker, 3,4-dimethyldecaine. I can, but we haven't gotten to those type of problems yet. Would you? Wait, Joanna, you're an organic one, right? It is a powerful play. You guys don't want to talk to me right now with my mouth. At least I didn't put onions in it. Okay, I can absolutely show you how to draw 3,4-dimethyldecaine, but if you're an organic one, we haven't gotten there yet. That's chapter 3 stuff, so the old exams online went through chapter 3 instead of through chapter 2. But I can show you real quick because it is real straightforward. So if I need, let's see, decaine, That's 10 carbons, right? So 10 carbons. And then 3,4-dimethyl would be 1, 2, on the third carbon there's a methyl group, and on the fourth carbon there's a methyl group. That's it. But that won't be on your exam tomorrow. It's okay. It's easy though, right? Can I draw another resonance? As long as you guys don't call it Renaissance or whatever you guys were calling it. Let's see. So Joyce wants another example of resonance. Let's see if I can do one with what I got here. Change this to a nitrogen, so we've got some electrons. And then that's not what I'm looking for. You guys will soon see that ChemSketch is not spectacular, but it's free. So that's the one that I use at home, and that's the one that I use with you guys. Okay, so here's a problem. I'm just going to cut off the end of it since we can't do any resonance over there. And I'm hoping you looked at that and said, yeah, we can't do resonance over there. So I will give you a couple minutes to work on this, Joyce, and anybody else that wants to work along. Make sure that's in frame. Yeah. And then also, this is new for y'all, a lot of you, at least, my channel. So let me explain a couple things. Number one, I usually have at least one dog with me who may or may not talk or bark or whatever. Number two, there is a delay, and it kind of depends on your computer. You can have two computers in the same room that will stream at different times, but it usually has about a 30 to 60 second delay. Takes time to transfer information. And then lastly, pardon me, I have about 8 different computer screens open on my computer, windows open on my computer. So sometimes it takes me a minute to pull up the text box to see that you've been asking questions and things like that. So just be patient with me. I do what I can. It's not a perfect system, but it is much better than what we've had in the past. So, all right. So Joyce, hopefully you got a little somewhere on that one, and anybody else that's kind of working along with me on this. This nitrogen here has a negative charge on it, and so that means it has an extra lone pair of electrons. There are ways of adding them into ChemSketch, but it kind of takes a little bit of time, so we're just going to act like we see them there, okay? Now what I can do, actually, is I can take this, drop them in Paint, and then move my window. Oh, that looks terrible. That resolution is not good. Okay, that's what we're going to work with. I know you guys can't see what I'm talking about. There we go. So now instead of being in a drawing program, a chemical drawing program, I just have it in Paint because I have a touchscreen monitor, and that works pretty well just to show stuff. So if I have, and let's put these in red. Oh, those are going to be hard to see. Let me make something bigger. And, whoa, okay, that's too big. 1, 2. Why won't it let me just put 2 dots? Okay. There we go. Sorry about that. Okay, so these electrons can move in and form a bond between the carbon and the nitrogen. That would make this carbon right here that I just drew a line through, that would make that have 5 bonds. So we can break that and put it as a lone pair on the nitrogen or on the carbon next to it. So that would be one resonance structure. Would be to have hydrogen, nitrogen, double bound now to a carbon. That carbon has a hydrogen on it. And again, if you need to show this in full form like this, do it. Do whatever you have to do to get the problem right. That's all I care about. I will have scrap paper on my desk tomorrow, so you guys will have plenty if you need it. Oh, shoot. Okay. All right. So remember, if this one over here has a negative charge, then all the others have to have a negative charge too, or you made up stuff, right? You can't do that. So this one was negative, and now the new resonance structure is also negative, okay? Now, another thing I can do, maybe I'll change my color so you can see it, is that these electrons can come in and form a bond between the other carbons, because adjacent is a pi bond, and we can move lone pair electrons in pi bonds, right? So if I move that in there, then this carbon here has 5 bonds on it, and that can't happen. But again, I can break that pi bond, okay? So I can do that and put that as a lone pair on the adjacent carbon. Oops, too far. Put my resonance arrow. CH, CH3, double bond, CH3, single bond, C with an H on it, and a lone pair of electrons. Just gonna move that a touch over. CH3. Okay, so let me shrink that a little bit. There we go. So I know my handwriting is even worse on a screen like this than it is in real life, but hopefully that kind of makes sense. Hopefully you can see that and that's kind of clear. So Joyce, please let me know if that made sense. If I have the practice exam handy, can you do the question that asks you to convert the condensed formula into the skeletal structure? I don't have it on me, but I can do a couple of those with you, Ryan. And then Kenny's like, I just need to know if I need these. Kenny, those are the ones from chapter 11. Also, we talked about how to put a tosyl group on. And then in chapter 10, the alcohol to halide groups. Hi, Janae. Okay, so Ryan, you needed to do condensed structural formula, or a condensed formula into a structure. Gotcha. Okay, so let's start again. So one of the problems that people, let's see, can we see that? When I draw it, I have to then pull up my other window to make sure that it comes across looking right to you guys. Okay, so let's do like a CH3, CH, NH2, CO, that's an O, CH3. Okay. So intuitively, and your book does talk about this a little bit. I think it's in chapter 1. So intuitively, you might want to go across and just connect the things that aren't hydrogens. And that would be incorrect. So if you do that, you're going to end up with like this carbon that I just circled wouldn't have 4 bonds on it. And that would be problematic. You can't put a triple bond to an oxygen on there and then the oxygen have 4 bonds on it. So you essentially are having to decode what structures are possible based off the condensed formula that's drawn, okay? So in this case, the CH3, I think that one's probably pretty obvious. It should be. CH, okay? Now, look at this part, okay, that I just underlined. If I went and did an NH2, and then the carbon next to that, the carbon here has a problem, and the nitrogen there has way too many bonds also, okay? So that doesn't work, but it would work if we attach the nitrogen to that carbon, okay? So then carbon, and that has an oxygen on it. So again, if I did this, hopefully you're like, that can't happen either because this carbon now only has 2 bonds. So that's not right. And next to it, we can't fit more bonds because of the atoms that are there. But what we can do is put a double bond to an oxygen and a CH3 next to that. So that is a perfectly reasonable structure that I'm able to look at and see that. So if you remember in general chemistry, a lot of the way that you would see acetic acid written was something like that, CH3COOH. And that's another example where it's kind of understood that you know the molecule can only look a certain way. So that just takes practice. Hopefully that makes sense. Let me check my chat box to see if that's making any sense. Okay. So Ryan, let me know if that makes sense. And if you have more questions, ask me about those. Okay. Austin, can I give an example of a molecule that has different bond types and how you recommend labeling the different bond types on a calculus structure? So there's actually a problem almost exactly like that in your book that was in the assigned homework. So really, if you think back to general chemistry and you're thinking about any of the polyatomic ions you had to memorize back then when it was terrible, right? So like if I have sulfate, the sulfurs and oxygens are all connected with covalent bonds. Yes? Yes. I'm going to assume you're agreeing with me. If I have sodium sulfate, those oxygens are counterbalanced with ionic bonds, or ionic interactions if you prefer to call them that. Sorry, my nose itches. Like that. Okay? There's lots of these, right? So sodium hydroxide. Sodium has a positive charge. OH. There we go. Now something you don't want to do, ever, and I see some people doing this, is they'll do something like that. Potassium hydroxide. The potassium is not covalently bound to the oxygen on the hydroxide. You know that, I know that, Onyx Dog knows that, we all know that. So don't draw an ionic bond as an actual covalent sharing of bonds. That convention is very specific just for covalent bonds. But you could probably, sodium acetate, potassium hydroxide, ammonium chloride, right? That's an example where the polyatomic ion is positively charged, so it's a cation instead of an anion. My dog is panting, so if you hear her, I'm sorry. And so you just show those charges, and those charges are basically implying that they're, ionically held together. So, Austin, let me know if that makes sense. And I'm going to eat another chip. Rihanna Bowling. Janae, why did you get a new name? Janae was such a good name. Every day. There's more than one of you in the room right now. You guys aren't watching me on the big screen, are you? That makes me eating a sandwich so much worse. Yes, it's assigned, but no, I don't turn it in. Or you don't turn it in. Because you need to learn to do it on your own for your own good. Plus, if you already know how to do an electron configuration, it doesn't make sense for you to have to do 25 of them in homework. If you don't get assigned homework that you have to turn in, you can prioritize your study time accordingly. You're adults, you can do it. At least that's what I tell myself. It also means you don't have to buy online homework. Aww. I miss Janae too. She needs to come back to campus. Janae's a good study buddy. She helped lots of people study, actually. Fruit fly. No, you don't get my tuna. When she decides to wake up. Yeah. Bailey would like to go over a constitutional isomer example. Okay. Hold on a second. I'm also checking. Just checking my emails to make sure nobody has sent me a question through there. Okay. Constitutional isomer example. Okay, here's one. Let me give you a different sort than the ones I've been giving you. Here's a molecule. It's called cyclohexene. It probably makes a little bit of sense because it's hexane, but with a ring and an alkene. So cyclohexene, they kind of go together. So what is the formula? And you should be able to look at it. You don't even need the formula to do it because you see a physical structure here. The units of unsaturation, which I will call a UOU for short. And then draw some isomers. work on that in a minute. If anybody has any other questions in the meantime, you owe you. Okay, so you should be done with that by now, with the formula part at least. So there's 6 carbons, and there's only hydrogens, but it's not a saturated molecule, right? It's got a ring and a double bond. So it's got, let's see, there's 2 hydrogens, 2, 2, 2, 1, and 1. So 2, 4, 6, 8, 10. And looking at the structure, you should know that it has 2 units of unsaturation, right? We don't even need, I mean, we could work out the formula here to do that, but we don't need to, because we can look and see it has a ring and a pi bond, which makes 2 units of unsaturation. So let's come up with some isomers that have 6 carbons and 2 units of unsaturation. So, and there's not like one right answer for this. There's lots and lots and lots of possible answers for this. Move that up here. Okay, so 6 carbons. I'll just draw 6 carbons in a row, and I need 2 units of unsaturation. Bingo, got one. Then just 2, right? So 6 carbons. Sure, 2 units of unsaturation. Let's make them different than the last ones. Put one there, one at the end. Those are 2 isomers. They're not connected the same way, right? Instead of having a ring with 5 or 6 carbons, let's do one with 5. Okay, but we still need 1 carbon, so I can put one there. Or 5 with a ring, and I could put one there. It's a different molecule. The methyl's not connected to the part that's the alkene anymore. It's connected to a different part. We could do it again and put one there. That's technically a different molecule as well. I could make something branched. So instead of having 6 carbons in a row, let's do 4 carbons in a row, and then 2 carbons on the sides, and 2 units of unsaturation. I could also do 2, 4. Yeah, this would be funky, but you could do that one, 2 rings. That would be 1, 2, 3, yep, 6 carbons and 10 hydrogens. I could do one that looks like a house with a tip on the top. So all I'm doing is just randomly writing down however many carbons, and then I basically add in units of unsaturation. Right, that's really all you have to do. I did not count a single one of those numbers of hydrogens because I don't have to. As long as you have the right number of carbons and the right number of units of unsaturation, you're not going to get it wrong. Okay, so I'm going to have you do another one. So let's do C3H5. Chai. I think that will give us a structure. Yes, okay. So with this one, you can go ahead and work on the units of unsaturation. So if I look at this, I think, okay, 3 carbons, so 2 times 3 plus 2 is 8. And then I subtract 1 because of the iodine. So for a fully saturated molecule with 3 carbons, I would need 7 hydrogens. You notice I only have 5. So 1 unit of unsaturation. Okay. So that's just kind of how the math works for that. I'm going to take that, delete it. So 1 unit of unsaturation, 3 carbons. So, okay, 1, 2, 3. 1 unit of unsaturation and an iodine. 3, 1 unit of unsaturation, and an iodine. 3 carbons, 1 unit of unsaturation, 1 iodine. Hopefully you're seeing how I'm doing this. Let me pull up my chat box. Let me know if this is making sense, folks, because nobody's commenting right now. Okay. Is there another option? There is. In this case, I could put a ring, because 3 carbons can make a ring. Can't do it with 2 carbons, but I could do it with 3. And add an iodine. So that would be 1, 2, 3, 4 isomers for this formula. That's basically all you can get with this one, I think. Looks right. But there you go, 4, pretty fast. So let me know if that makes sense on how I'm doing that. Don't try and like make it this like weird magical experience, like balancing equations or anything, because it's much more straightforward than that. You really, as long as you can just get a skeleton down, with the number of carbons and other atoms that aren't hydrogen, and then put in the units of unsaturation, you're good. Okay. Wrong screen. I bought my car out of a vending machine, and they gave me a cup. It's a very weird experience, I have to admit. Okay. Yes? Absolutely, Caitlin. So if you have 2 units of, so the last molecule only had 1, but if you have 2 units, then you can absolutely do a triple bond. So if I have, let's see, so that would be 1, 2, so C4, H, 3, 4, 5, 6. Yeah. So a fully saturated molecule would be C4H10. C4H6 would have 2. So this would be a possibility on that. You could also have, let's see, let me draw it this way. You could have it where the triple bond is in the middle, like that. And then, you have a couple other options, because you could also have a ring with a double bond in it. That would be another option for that. This one, you're a little bit more limited. Let's see, that would be 4 carbons. Yeah, you couldn't do that. But, there would be quite a few options here. You could have CH2, double bond, C, double bond, C, H, CH3. Yeah. So something like that. We could move the double bonds around, but you could always put on a triple bond as well if you're looking for 2 units of unsaturation. Now, there is a problem in your book. It didn't go through for some reason. Do elimination reactions use polar protic or aprotic solvents? So it'll depend on the type of elimination reaction, E1 or E2. So the same things that do SN1 will do E1, and the ones that do SN2 will do E2. But I haven't really specified for the elimination reactions because your book doesn't, Kenny. Okay. So let me get back to Caitlin. Caitlin, did that make sense? And then, wait, you guys had a fire drill? Yeah, they do use them. Okay, great, Caitlin. And then Ryan wanted a hybridization example. So, there are a lot of these in the book also. Yeah, I'll leave it like that. So, I don't know why, for me, every time I have this type of functional group, it's called a cyano group or a nitrile. I always draw the carbon part out, almost always. You don't have to. If you're looking at this like, why does she draw that? It's because I'm quirky like that. So on this molecule, go ahead and use I'll go ahead and use yellow. So I want you to try and find and label all of the SP hybridized. Those should be easy to find because there's very few of them. My husband's laughing in the background. I don't know what he's watching. Yeah, Kenny, somebody in your dorm's being a jerk. So SP hybridized, the way I look for that is I look for any atom that has 2 pi bonds. Okay. So this carbon has 2 pi bonds and the nitrogen has 2 pi bonds. I don't know if you want to number them 1 and 2. You can if you want, if that helps your brain. But both of those are sp2 hybridized because they both have a triple bond, basically. Alternatively, you could have 2 double bonds. So if I have a carbon dioxide molecule, that carbon is also sp hybridized. Okay, so it doesn't have to just be a triple bond, but just 2 pi bonds in general going to one atom. Now, let's do green for sp2. Find those. I just scared Onyx. Oh my gosh, you're shedding so bad. What is that? Stretch your little legs. All right. So for sp2, I'm just looking for things that have 1 pi bond. And by things, I mean atoms. So you'll notice I circled the carbon and the nitrogen, not the carbon-nitrogen bond, right? Hybridization is specific for an atom, all right? So for sp2, this carbon has 1 pi bond. This carbon has 1 pi bond. This carbon, that oxygen, Also, these oxygens on the other molecule that I happen to draw in the corner. Let me make sure you can see those molecules I'm drawing. Okay, good. So hopefully you got that far with me and you see what I'm talking about. Now, let's do purple. sp3. Pardon me. So go ahead and find anything that's sp3 hybridized. Okay. So for that one, when you're looking for sp3, you're basically looking for an absence of pi bonds. So my oxygen, and we're not looking at hydrogens, right? Like this hydrogen here technically has no pi bonds. The hydrogens don't hybridize. So we have to look at everything that we know can hybridize. So oxygen, carbon, carbon. Fluorine is a halogen, and we're making the assumption for this class that halogens don't hybridize. Okay, so that brings us to a question of how many unhybridized atoms there are. So for that one, we're basically having to count up every hydrogen and halogen, right? Because those are the ones that hydrogens can't hybridize, and we're assuming that halogens won't for the sake of this class. Okay, so unhybridized, that has 2. That one doesn't hybridize. There's a hydrogen on there. There's 3 on there. 1 there. 2, 3. There's another one attached there. So add those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that 15 atoms? So I can double check my math on that. But 15 unhybridized atoms on this molecule. Okay. Now, let's go through and look at this and think about things like geometry and bond angles and things like that. So I want you to remember that these sp hybridized are all going to be 180 degrees approximately with linear geometry. And you can see I drew that there with 180 degree angles with linear geometry. Okay. The sp2, those need to be about 120 degree angles, and they have planar geometry. I'm abbreviating that. So that's kind of hard to show through here. But in a 3-dimensional structure, you would see it a lot better. But I need you to at least know that that's 120 degrees with planar geometry. And then the sp3s, I'm running out of room to write, are about 109.5, give or take, and they have tetrahedral geometry. Okay, so those are important points to note. Other hybridization questions? I could say which one of these atoms has the most S character, and those would be anything that was sp hybridized. So the carbon and the nitrogen over here have the most S character. Okay. And then the least S character would be anything that had the sp3 hybridization. That would be a lot of stuff to circle. Could talk about like how many orbitals you get, right? So if you add 2, you get 2, right? You have to have conservation of orbitals. Those are all just kind of the kind of concepts that I need you to know for tomorrow. So hopefully that made sense to you, Ryan. Bailey was really worried about the guy down there. What guy down there? What are you talking about? The carbon on the bottom. I wasn't looking at the chat. I don't know what's going on. Did I answer questions or are you confused? Guys, talk to me. Let me know you're still out there. It says there's 9 of you. Is there anybody out there? Oh, good catch. For shame, Dr. Man. For shame. Is that better? I guess I got on a roll and just left that guy off. Now I see what you were talking about. Kenny was talking about a fire drill and you guys were talking about somebody being worried about a guy, and I was like, what's going on? You guys are all in different places, I guess. What's up? Test is written and printed. It is ready to go. Check my email again, see if anybody... I have one student that emailed me, but I think they just want me to email them back. Austin, I will. Let me just finish sending this text real quick, or this email. Follow Zav's rule. Okay. So, breaking down the pKa factors on an acid. Yeah, let's do a couple of those. So, let's do... Ooh, let's pick an amino acid. Let's get really exotic here. So, I'll give you one that you haven't seen before. So that way it's fresh and it's not just kind of reiterating what you've seen. This one's not on your number line, but I'll give it to you so we can work it through using those same 5 principles that you're talking about. Okay. So... So amino acids have an amine and an acid. That's where they get their name. Okay. So this is the amino acid tyrosine, just in case anybody cares. It has a carboxylic acid functional group on it, right? It has a pKa of about 2 to 4. It has an amine, and in the body, it looks like that because it's in water. And so the protonated version has a pKa of about 8 to 10. And then this one here is not actually what you normally would put for an alcohol. Okay, so normally our alcohols are around, usually about 16 to 18. They can go down to 15, around the same as water, but I put 16 to 18 so you guys can distinguish them. So this one's pKa is actually around 10. So my question to you, okay, and I'm going to redraw this to make it a little bit easier. So this one here is 10. This one here is 16 to 18. So my question to you, classroom, wherever you are, is why does the one up here have a lower pKa? Right? And so to answer these questions, you have to think about those 5 factors, right? But those aren't, and this is a thing that people do. They just try and memorize them without really thinking about what they mean. So if you're having trouble understanding them, it's probably because you're looking at them as a checklist of things to memorize. And I'm not accusing anyone of that. It's just I've seen that a lot. But so what you need to think about is what the acid form looks like, and then what its conjugate base looks like. Okay. And same here. Okay. So when you're looking at these kind of problems, you're essentially saying, especially in this one where I'm having you compare 2 molecules, why is this one on the top so much better as an acid? Why is it more likely to donate that proton when there's a base around? Okay. So let's think of those 5 factors, and I can actually type these in. So when I look at this molecule on top, is my acidic hydrogen, right? Shoot, what did I do? Is my acidic hydrogen here on an electronegative atom? Yes, it's attached to an oxygen. So the product is stabilized because a negative charge is being put on an electronegative atom, right? So you're having to look at the starting material and the product, right? That's essentially why would this reaction happen, okay? Number 2, is size a factor? Is the proton attached to a large atom that can stabilize its negative charge because it can disperse it over a fairly large area? No. Oxygen's pretty small, right? And again, this is all relative, but oxygen's quite small in comparison to something like bromine or chlorine or iodine. Is there a charge that we take off by donating a proton? In this case, no. We see it with hydronium, H3O+, and we see it with protonated amines. In both of those examples, you have a positive charge, and when a base reacts, there's no more charge. So in that case, that helps stabilize it, but that's not a factor on this particular molecule. Inductive effects. Are there any inductive effects? Meaning, is there any kind of electronegative atom elsewhere in the molecule that can kind of help draw in electron density? And the answer to that is no. And so lastly, the last one is resonance. Is there resonance that can stabilize the product of the reaction? And the answer for that is yes. Okay, so if I'm looking at this particular molecule and I'm looking at resonance structures, this negative charge can come in and get put on a different carbon. Okay, well, on a carbon rather than on an oxygen. Okay. That didn't move, that didn't move. All right. There's my lone pair of electrons. Those electrons can move and form a bond between these 2 carbons, and these can come out and make a lone pair. Okay. So there are several resonance structures here for this. There's actually quite a lot of resonance for this. Now let's compare that to the one down here on the bottom. Is there electronegativity? Yeah, it's still attached to the same type of atom in oxygen. Did you actually hear that? I think she can hear sneezes. Okay, electronegativity, yes. There's no charge factor, there's no size factor, there's no inductive effects, but there's also no resonance. Okay? There's no pi bonds to move around the ring. So that's actually why this this one here has such a low pKa, is because the conjugate base, the product of the reaction, is stabilized through resonance. What? I just pulled this chat up. What have you guys been talking about? An acid-base reaction. Top one has Renaissance, Steven says. He was right. It is very artsy. You guys are ridiculous. Okay, so an acid-base reaction, I can do that for Hannah. I bless you all. Onyx blesses you all. Here's Onyx Cam. Ah, Onyx! It's not a video chat without a dog shot. It just depends who's sitting next to me. Okay. I'm going to do this one. Go back to image. Okay. So let's take... Oh shoot, what have I done? Okay. So here's a molecule, and plus sign, plus, and another molecule. So let's do another nitrogen. Nitrate ion. Okay. And arrow. All right. So go ahead and start working this. I'll put a little box down here for pKa, and I'll put a little box down here for whether it's the acid, the base, the conjugate acid, or the conjugate base. And we might have to change that arrow, but I'll leave it there for now. It's kind of a placeholder, because otherwise it just looks weird, doesn't it? All right. So I'm going to actually draw arrows for this one. Okay. So hopefully you looked at this and you said, that is a nitrogen with a positive charge on it with an extra proton. That one has a pKa of about 8 to 10 because it is a protonated amine. Okay. If you got there, I'm happy. This one might have been a little harder for you. If you look at this, it's a nitrate anion. Is there a hydrogen on there? No. So there's no hydrogen to donate, which means there can't be a pKa because there's no Ka, because there's no equilibrium constant for an acid if there's no proton to donate. Okay, so that one has none. I'll just draw a little dot, dot, dot. Okay. So looking at this, the one that has a pKa is going to be your acid, right? And then this one here is my base. Fantastic. So the way this works is your base is what kind of attacks the proton on your acid. So I will go ahead, and I don't usually start covering this until a little bit later on, but here we go. But the oxygen, the lone pair of electrons on the oxygen, will grab that hydrogen. And why is that not? There we go. Okay. And when that happens, I have to break that nitrogen-hydrogen bond, because otherwise that nitrogen, well, the hydrogen would have two bonds going to it, okay? So I'm going to break that off and put that on the nitrogen. What have I done? That's a really bad arrow. Tiny. Okay. So for my structures then, what I get, I did not change my CH3 groups down here. Those have stayed the same, right? And I actually did not change the two methyl groups on my nitrogen, but now my nitrogen is missing that proton because I took it off, right? Rather than nitrate did. So what does my nitrate look like then? And now you'll notice that what my molecule is nitric acid. So what I started off with was the conjugate base of nitric acid. Put another plus sign. Come up with my pKa's. So here my pKa of just a regular amine is in the 30s, give or take. And nitric acid is a strong acid, so we know that one's less than 0. Okay. I can go ahead and write down that the amine is my conjugate base, and my nitric acid is my conjugate acid. Okay. And then we need to think about the arrow. Where are you going, booby? What's going on? Brandon, I have an elderly dog alert. Can you help me? What are you doing? Sorry. Get your face in the camera. Brandon, I need help. There's like an ear. There's an ear. I think she wants down. She can't jump anymore. Okay, so amine, nitric acid. There we go. Okay, so we were talking about the arrow. She has started to migrate and move around and act uncomfortable. Can you get off the bed? I'll get picked up. Yep. Okay, maybe I was wrong. Maybe she didn't want off. Her and Twinkie need dinner. The life in the house with 3 dogs. Okay, I apologize. So if the nitric acid is a strong acid, which we know it is, right? We can only really expect the reaction to go one direction. We won't really have an equilibrium set up, and it'll go towards the side with the weaker acid, so the amine over here. Okay? Sorry, that was a long time to get through that. Should we be able to protect the numerical pKa? So No. Um, as far as the numerical pKa goes, you basically have to experimentally determine what that is for any given molecule. There are other factors that go into it, like what else is in the solution, which solvent you're using, right? These are all basically in water, which we're not even always using in this class when we do reactions later on in the semester. And that's why I give you guys really just approximations, because we know certain functional groups through experimentation. We know that certain functional groups kind of exist in a little range. And there are molecules that have those functional groups that can exist out of that range, right? So with the fluoroacetic acid example I gave you, TFA, trifluoroacetic acid, it was my example of inductive effects in your notes. And that one is a really good acid. It's not a strong acid, but its pKa is about 1, which is much lower than the other carboxylic acid functional groups that you see. So there can be times, or like that example that I just had with the benzene ring with the alcohol on it, there are times where you can have other factors that can draw the pKa down, or even some that could raise it. But overall, I just need you to know kind of approximately where they would be based off the number line I gave you in class. We can do a lot of chemistry, and you guys have seen that. We can do a lot of chemistry by just learning a few of those. Okay, so that kind of helps you get that purpose. Linux, how can I tell what? Can you be slightly more specific? I didn't have my chat box up when you when you posted that, so I don't know exactly what you were asking because I don't know what I was looking at or what you were looking at when that came up. So from I have up, on the right you have nitrogen attached to, yes. So any kind of nitrogen with a positive charge and a hydrogen on it is going to still be considered a protonated amine. And we'll get more into that in future classes, but not yet. Okay. So Austin, this might make it a little bit more sense. I don't know. Let's see. This is really what a protonated amine looks like, where you can have 3 of anything really, as long as you have 1 hydrogen. So I put hydrogens in R, like 1 R and an H2. But really it can be anything else. As long as you have 1 hydrogen on there and a positive charge, you can have a protonated amine. That is a protonated amine. And Angel, I do not have that sitting in front of me. Hold on a second. I don't know if you guys saw my little video that I posted before your all's the organic 2 session or organic 1 session that started at 8. I got my computer fixed like right in time to start that, but I worked for over an hour to try and get it to work. So my organic 2 review session kind of got, and I posted a short live web of that. It was being real spatial. So Angel said exam 1. Number 3, 2018. I saw what you wrote, but I'm going to go ahead and pull it up. Okay, so how many dichlorinated products could you get from the following reaction? There are some problems very similar to that, and I think chapter 6 in your book, which is where free radical halogenation gets introduced. But essentially, you're just looking for how many times could let me make sure I have the right screen up. How many times, so dichlorinated would be 2 chlorines, right? So how many times could I have, like how many distinct molecules could have 2 chlorines on them if butane is your starting? So that's really just a factor of kind of playing around. So if I have butane, let's see. I'm just going to copy and paste this a few times. Okay, so where could my chlorines go? Maybe on one of the end carbons. That works, right? I could get on a 1 and 2 substituted type deal. I could have a 2-2 substituted. I could have a 1-3 substituted. I could have a 1-4 substituted. So I'm just kind of playing around with how many different combinations there could be. Remember that if you had a 4-4, that would actually be the same as a 1-1, right? Because it could flip. So I think that might be, yeah, you could have those 5. With methane, you could have 1 chlorination, 2, 3, or 4. So you could have 4 different products with methane. But I was just asking for dichlorinated products, so you could actually get mono, di, tri, tetra on these. That's why I don't particularly like that reaction a whole lot. Will there be a similar question? I'm not telling you what's on the test, Kenny. Weenie. Weenie. Angel, can you let me know if that made sense? I know that it's frustrating because I can only answer like 1 question at a time, and I have a lot going on around me at my house. But yes, that's Kenny. He's not in the class, Janae. He's in organic too, but he's just along for the ride today. He also always wears a hoodie, frequently listens to music in his ears. Awesome, Angel. Okay, well, it's like 9:15, folks. If there are any more pressing questions, you can send them to my email. Angel, if you have any others, I can take any more from you and Kenny or any other Organic 2 people, since I didn't get any, specific time with you guys, but I kind of need to get off here by about 9:25. I only have a few minutes left. What is a vinyl radical? That one's in your book. Look it up. I can just Google it too. Let me see what Google comes up with. Yeah, if you do Google image search, you'll see a lot of examples. And in fact, one of them from sites.google.com is labeled radicals, and it has Vinyl, benzyl, and alkynyl, and allyl. It's got a bunch of them. So you can kind of see what those look like. So, Abby, I've already done a lot of those questions, and you have several in your notes, so I don't want to just keep doing those over and over and over again. But if you have some specific questions about them, I'm happy to answer those. Okay, so feel free to ask like a specific question about those 5 factors and like a specific acid or something. It's a vinyl that doesn't listen to the man. It's a punk rock radical. Does anti-periplanar have to do with sigma bonds aligning for pi bonds? Linux, yes. So the anti-periplanar is the orientation it needs to be to undergo an elimination reaction. And so that's just content from Organic 1 on what an anti-periplanar looks like. You usually see them drawn as a Newman projection. How can we decide if electronegativity affects it? If there is electronegativity, it affects it. So, and I talk about that a little bit earlier in the video. If there is an electronegative atom with a hydrogen on it, so think oxygen, nitrogen, fluorine, chlorine, right? Those are our main electronegative atoms. If those are connected to a hydrogen, that hydrogen is more likely to be donated because that atom can handle the incurred negative charge from removing the hydrogen. Okay. And you'll notice the more electronegative an atom, the lower the pKa goes. So a regular amine is in the 30s, right? But compare that to a carbon group in the 50s. Then with oxygens, it goes all the way down into the teens. And then with fluorine, it goes down to 1, right? The pKa of hydrofluoric acid is about a 1. And those are all about the same size, right? They're all next to each other in the periodic table. So if a hydrogen is on an electronegative atom, that will make it more acidic. So it will decrease the pKa. If it removes a charge, so if you had something with a positive charge and taking a hydrogen off or a hydronium ion relieves that charge, that makes it more acidic. So I was just saying, Anna. So think like hydronium ion. Let me pull up my, which one am I doing? Check here. Okay. Pop goes the weasel. Okay. So if I have, like the 2 examples that you'll usually see with a positive charge is if, whoa, that is very yellow. That's a lot of special. All right. Why? Oh, I see. There we go. All right. There we go. That looks better. So let's say I have an oxygen. I don't care if it's water or hydronium or protonated alcohol. When I take that proton off, I get rid of that positive charge. That makes it more likely to donate that proton because it wants to get rid of that charge if it can. The other example you'll see a lot is with a protonated amine. So that has a positive charge. And when we go through an acid-base reaction, we lose that positive charge, right? So that is another way that, that stabilizes that molecule to get rid of that charge. So it's all about looking at the starting material and the product and figuring out which ones are going to be more stable. Okay, like what factors are going to stabilize it. I gave you 5 you can choose from. So it's all about just looking at that and being able to kind of pick which ones make sense with that. Hopefully that makes sense. Abby and Hannah, does that make sense? Require confirmation. Dr. Mann requires confirmation that that made sense. Okay. Yes. You are absolutely welcome, ladies. Okay, so it's like 9:20. It's getting kind of late, and I need to do things like take a shower and stuff so I don't smell y'all out of the room tomorrow. My little dirty secret you just found out. I'm a nighttime showerer. I don't like using a blow dryer in the morning. Anyway, I will go ahead and hop off here, but like I posted in the other like little 2-minute my stuff's not working video, I will be able to answer questions through email until about 1:30, and that's when I'll go to bed. So if you have any more questions that you think while you're studying tonight, feel free to email me. I'll try and get back to you as soon as I can. I know sometimes office hours are hard to get to, so, you know, it's okay. I know that, you know, a lot of you prioritize like the night before for like extra study time. So, you know, I try and be available for you guys to do that. So anyway, I'll go ahead and hop off here. But again, email me. If it's in my mailbox by 1:30, I should answer it. And if not, I will see you in the morning, okay? So deep breath. You can do this. We should have like a YouTube meditation session where we all just like deep breathe and make our hair look funny. And there we go. So I'll see y'all tomorrow, okay?